In the grand, silent theater of the cosmos, we often gaze outward, seeking the strange and the magnificent in distant galaxies and nebulae. We imagine alien worlds and cosmic cataclysms billions of light-years away. Yet, the greatest secrets often lie closer to home, hidden in the familiar darkness of our own solar system. This is a journey that begins not in a faraway galaxy, but at the frozen, uncharted edges of our own cosmic neighborhood, a place we thought we knew, but which is proving to be as mysterious and full of undiscovered worlds as any distant star system. It is a detective story on a cosmic scale, where the universe leaves subtle clues, a faint glimmer of infrared light, the inexplicable wobble of a distant object, a chemical fingerprint in a plume of ice, and we, through the painstaking process of science, attempt to piece them together. Each new discovery, each solved puzzle, doesn't just add a fact to our collection. It forces us to rewrite the entire story, to reconsider our place in a universe that is vastly more complex, more violent, and more wondrous than we ever imagined. Our journey starts in the outer darkness, in the hunt for a ghost. Beyond the orbit of Neptune lies a realm of icy darkness, a vast, frigid frontier known as the Kuiper Belt. For decades, we saw it as the solar system's desolate attic, home to dwarf planets like Pluto and a scattered population of frozen debris left over from the dawn of our system. But in 2016, astronomers Konstantin Batygin and Mike Brown noticed something strange. When they mapped the orbits of the most distant objects in this region, a handful of them, these trans-Neptunian objects or TNOs, were behaving inexplicably. They weren't moving randomly as they should. Instead, their elongated orbits were all clustered together, pointing in the same direction, tilted at the same angle, as if they were being shepherded by the gravitational hand of a massive, unseen player. This was the first piece of evidence for what they nicknamed Planet 9, a ghost in the outer darkness. The hypothesis was bold. A massive planet, a true ninth planet, must be lurking in the far reaches of the solar system, its gravity shaping the paths of these smaller TNOs. The theoretical properties of this world were stunning. It was predicted to be a super-Earth or a mini-Neptune, a world with 5 to 10 times the mass of Earth and a radius 2 to 4 times larger. Its orbit would be highly eccentric, taking it hundreds of astronomical units from the Sun, far beyond Neptune, on a journey that could last thousands of years. The existence of such a planet would be transformative. Surveys of planets around other stars have found that super-Earths are the most common type of planet in the galaxy, yet our own solar system seems to lack one. The discovery of Planet 9 would mean our solar system is not so strange after all. It would make us look more normal. One compelling theory, the 5-planet NICE model, suggests our solar system may have originally formed with 5 giant planets, with one being gravitationally ejected into the far outer system during a chaotic primordial dance. Planet 9 could be this long-lost sibling, a remnant of our solar system's turbulent youth. The hunt was on. Astronomers began a painstaking search, knowing that a planet so distant would be incredibly faint, reflecting very little sunlight. The best hope was to detect its own internal heat, which would make it glow faintly in far-infrared light. Researchers delved into archival data from infrared space telescopes like the Infrared Astronomical Satellite, IRAS, and Japan's Akari mission, looking for a tiny, moving dot of warmth against the cold background of space. Recently, a team led by astronomer Terry Long Fan announced a promising candidate. By comparing surveys taken 23 years apart, they found a faint object that appeared to have moved a tiny distance, just 47.4 arc-minutes, consistent with the slow crawl of a massive planet in a distant orbit. For a moment, it seemed the ghost might have been found. But this is where the scientific process reveals its true, self-correcting power. The initial hypothesis, based on the statistical clustering of TNO orbits, led to predictions about the planet's properties. Those predictions guided the search, which led to the identification of a candidate. But the story doesn't end there. Mike Brown, one of the original proponents of Planet 9, analyzed the potential orbit of this new candidate and delivered a stunning verdict. It is, in his words, 100% not Planet 9. The candidate's inferred motion suggests an orbit that is highly inclined, almost perpendicular to the plane of the solar system. Such an orbit could not produce the specific gravitational effects, the shepherding of TNOs, that the Planet 9 hypothesis was invented to explain. What seemed like a failure was, in fact, a crucial step forward. It ruled out a possibility, refined the search parameters, and sent theorists back to their models. Some surveys, like the Outer Solar System Survey, OSOS, have even suggested the original clustering might be an illusion, a result of observational bias and small number statistics. The truth remains elusive, a testament to the fact that science is not a straight line to discovery, but a winding path of hypothesis, observation, and constant refinement. The hunt continues, with future hope pinned on the Vera C. Rubin Observatory, set to begin operations in 2025. Its unprecedented survey of the southern sky may finally find this hidden world, or prove its absence once and for all. And the public can join the search through the NASA-funded citizen science project, Backyard Worlds. Planet 9 poring over infrared data for the faint signature of a world that may or may not be there. The mystery of Planet 9 shows us that even the very structure of our solar system is an open question. But it is not the only one. Closer to home, nestled between the orbits of Mars and Jupiter, lies another region long shrouded in myth and misunderstanding, the asteroid belt. Science fiction has painted a picture of a dense, chaotic field of tumbling rocks, a navigational nightmare for any starship. The reality is far different. The asteroid belt is a realm of profound emptiness, its material so thinly distributed that numerous spacecraft have traversed it without incident. The old theory that the belt is the shattered remains of a destroyed planet has also been debunked. The total mass of all the asteroids combined is a mere 4% of the mass of Earth's moon, far too little to be the remnant of a major planet. The true mystery is not what destroyed a planet there, but why one never formed in the first place. For decades, the classical view or the depletion theory held sway. This model posited that the region initially contained several Earth masses worth of planetesimals, the building blocks of planets. But the immense gravity of nearby Jupiter, especially if it migrated during the early solar system, acted as a cosmic bully. Its gravitational pull stirred the planetesimals into high-speed, destructive collisions, preventing them from gently accreting into a single large body. Instead, they ground each other down, and Jupiter's influence ejected over 99.9% of the original material, leaving behind only the sparse remnants we see today. However, a new and compelling hypothesis has emerged that flips this story on its head: the accumulation theory. This model suggests the region started largely empty and was populated over time by objects scattered from other parts of the solar system. Objects that formed in the hot, inner solar system were kicked outward, while icy bodies from the cold outer regions were nudged inward. The asteroid belt, in this view, is not a graveyard, but a cosmic meeting point. The most powerful evidence for this new model comes from the two largest residents of the belt, Vesta and Ceres, visited by NASA's Dawn mission. Their compositions are starkly different. Vesta is a dry, rocky world covered in volcanic basalt, a composition that suggests it formed in the hot, inner solar system much closer to the Sun, before being scattered out to its current location. Ceres, in contrast, is a water-rich dwarf planet, its icy composition linking it to the frigid outer solar system where it likely formed before being implanted into the belt. The asteroid belt, therefore, is not the remnant of a single failed world, but a cosmic Ellis Island, a collection of immigrants from all across the solar system, making it an invaluable and diverse record of our system's formation history. Just as this new picture was solidifying, the latest findings from the Dawn mission have introduced profound new puzzles. For decades, Vesta was the textbook example of a protoplanet, a planetary embryo frozen in time. But a recent, more refined analysis of Dawn's gravity data has revealed something startling. Vesta may not have a differentiated iron core, mantle, and crust as previously believed. This shatters our simple picture of planetary building blocks. Two new hypotheses are now being debated. Perhaps Vesta underwent incomplete differentiation, starting the melting process but never finishing it. Or, more radically, perhaps Vesta is not a protoplanet at all, but a massive piece of planetary shrapnel, the result of a colossal impact that blasted it off a much larger, growing planet in the chaotic early solar system. This would mean the meteorites we have from Vesta are not samples of a failed planet, but perhaps pieces of a lost world we have never seen. At the same time, Ceres has revealed its own treasures. Data from Dawn has confirmed the presence of organic compounds on its surface, particularly near a feature called the Ernetet crater. While some of these life-building molecules could have been delivered by impacting comets, new research strongly suggests an endogenous origin, that these organics formed within Ceres itself and were excavated by impacts. This implies the existence of a vast subsurface reservoir of organic material and some form of internal heat or chemical energy, making Ceres a prime target in the search for the ingredients of life. The story of the asteroid belt is a story of constant revision, with future missions like Lucy, which will visit the Trojan asteroids sharing Jupiter's orbit, and Psyche, which will journey to a unique metallic asteroid, promising to add new chapters to our understanding of this dynamic and surprisingly diverse region of our solar system. The discovery of water and organic materials on Ceres, a world that may have once harbored a vast ocean, provides a natural bridge to the even more tantalizing ocean worlds of the outer solar system. We move now from a world that might have had an ancient ocean to worlds that almost certainly have them today, hidden beneath shells of ice. Our first stop is Jupiter's moon Europa. The first hints of its secret came from the Voyager spacecraft in the 1970s. The images they sent back were puzzling. Europa's surface was remarkably smooth, lacking the heavy cratering seen on other moons, which suggested its surface was geologically young. It was crisscrossed by a vast network of dark bands and ridges. Most intriguingly, some of these cracks looked like pieces of a jigsaw puzzle that had been pulled apart, with dark, icy material flowing into the gaps, a clear sign that the surface was mobile and active. The definitive evidence, the smoking gun, came from the Galileo mission in the 1990s. As Galileo flew past Europa, its magnetometer detected a disturbance in Jupiter's powerful magnetic field. This disturbance strongly implied that an induced magnetic field was being created within Europa, something that could only happen if there was a deep layer of an electrically conductive fluid beneath the surface. Given Europa's icy composition, the most likely candidate for this fluid is a global ocean of salty water. High-resolution images from Galileo also revealed bizarre, jumbled landscapes called chaos terrains, which look like massive icebergs that have broken apart, shifted, and refrozen in a slushy matrix. Models suggest these features form above large, shallow lakes of liquid water locked within the ice shell itself. This is a crucial finding, as the collapse of these overlying ice shelves could provide a mechanism for transferring nutrients and energy from the surface down to the vast, dark ocean below, a process vital for making that ocean a potentially habitable environment. If Europa was a tantalizing hint, Saturn's tiny moon Enceladus was a stunning revelation. When the Cassini spacecraft arrived at Saturn, Enceladus was expected to be a small, inert snowball. Instead, in 2005, Cassini's cameras captured one of the most breathtaking sights in planetary science. Geyser-like jets of water vapor and ice particles erupting into space from deep fissures near the moon's south pole, informally dubbed tiger stripes. This discovery was revolutionary. We didn't need to speculate about an ocean. Enceladus was spraying its ocean directly into space for us to sample. And sample it we did. Cassini flew directly through these plumes multiple times, using its instruments to taste the composition of this alien ocean. What it found was a rich chemical brew, containing all the classic ingredients for life as we know it. It found water, of course, but also salts, carbon dioxide, methane, and a variety of simple organic molecules. Crucially, it also detected tiny grains of silica, which can only form when hot, mineral-rich water interacts with rock at temperatures above 90 degrees Celsius. This was powerful evidence for the existence of hydrothermal vents on the seafloor of Enceladus, environments strikingly similar to the deep-sea vents on Earth that teem with life, independent of sunlight. For years, one crucial ingredient remained missing: phosphorus. It is the least abundant of the 6 essential elements for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. But it is indispensable, forming the backbone of DNA and a key component of cell membranes. Then, in a landmark study, scientists analyzing ice grains from Saturn's earring, which is fed entirely by the plumes of Enceladus, detected sodium phosphates. The final piece of the puzzle had fallen into place. Enceladus now appears to possess all the primary chemical ingredients required for life. The existence of these hidden oceans on worlds far from the Sun fundamentally redefines our concept of habitability. The classical habitable zone is the region around a star where surface temperatures allow for liquid water. Europa and Enceladus are far outside this zone, in the deep freeze of the outer solar system. Their oceans are kept liquid not by the faint warmth of the Sun, but by internal heat generated by tidal forces, the constant squeezing and stretching they experience from the immense gravity of their parent planets, Jupiter and Saturn. This discovery opens up a vast new parameter space in the search for life. We no longer need to limit our search to Earth-like planets orbiting Sun-like stars. We must now consider the countless large moons that likely orbit giant planets throughout our galaxy as potential abodes for life. Furthermore, Enceladus offers a uniquely accessible target. While exploring Europa's ocean would require a lander capable of drilling through kilometers of hard ice, a monumental engineering challenge, a future mission to Enceladus could simply fly through its plumes with more sensitive instruments, directly searching for complex organic molecules or even the fossilized remains of microbial cells. It transforms the search for life from a passive act of remote observation into an active one of direct sampling, making Enceladus arguably the most compelling place to look for life beyond Earth in our solar system. Our journey through the secrets of space now takes us from the worlds orbiting our Sun to the suns themselves. Stars are the engines of cosmic creation, the furnaces where the elements of life are forged, and their life stories, from fiery birth to dramatic death, dictate the evolution of the universe. All stars, regardless of their size, begin their lives in the same way, as vast, cold, dark clouds of gas and dust known as nebulae or molecular clouds. Within these clouds, gravity begins to pull material together into dense clumps. As a clump collapses, the pressure and temperature at its center rise, creating a warm, glowing embryonic star known as a protostar. After a turbulent youth, often marked by powerful outflows of gas in what is called the T-Tauri phase, the core of the protostar becomes so hot and dense millions of degrees that nuclear fusion ignites. This is the moment a star is truly born. This ignition marks the beginning of the main sequence, the long and stable adulthood of a star, where it will spend roughly 90% of its life. During this phase, the star is in a state of equilibrium, with the outward pressure from the fusion in its core perfectly balancing the inward pull of gravity. The primary fusion process converts hydrogen atoms into helium, releasing a tremendous amount of energy in the process. A star's mass is its destiny. Low-mass stars, like the common red dwarfs, are frugal with their fuel, burning hydrogen so slowly that they can remain on the main sequence for hundreds of billions, or even trillions of years, far longer than the current age of the universe. Massive stars, in contrast, are cosmic gas guzzlers. They burn through their fuel with ferocious intensity and will leave the main sequence after only a few million years. The end of a star's life begins when it exhausts the hydrogen fuel in its core. For a star like our Sun, the cessation of core fusion causes gravity to win the battle, and the core begins to contract and heat up. This new heat is intense enough to ignite hydrogen fusion in a shell surrounding the now inert helium core. The energy from this shell fusion pushes the star's outer layers outward, causing it to expand dramatically. The star swells into a red giant, its surface cooling as it expands, giving it a reddish hue. Eventually, the core becomes hot enough to fuse helium into carbon. When the helium fuel is also exhausted, the star's life is effectively over. It can no longer generate enough pressure to support its own weight, and it sheds its outer layers into space, creating a beautiful, glowing shroud of gas called a planetary nebula. Left behind is the star's hot, incredibly dense core, a white dwarf. This stellar remnant, about the size of Earth but with the mass of the Sun, will simply cool and fade over billions of years, eventually becoming a cold, dark object known as a black dwarf, though the universe is not yet old enough for any black dwarfs to exist. Massive stars, those more than about 8 times the mass of our Sun, face a far more spectacular and violent demise. After they expand into a red supergiant, their cores are so massive and hot that they can continue to fuse progressively heavier elements. A series of fusion stages creates concentric shells within the star, like layers of an onion, fusing helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, and finally silicon to iron. This is the end of the line. The fusion of iron does not release energy. It consumes it. With its energy source gone, the outward pressure that supported the star vanishes. In a fraction of a second, the iron core collapses under its own immense gravity, triggering a cataclysmic explosion known as a Type II supernova. This titanic blast rips the star apart, blasting its outer layers, enriched with all the heavy elements it created during its lifetime, out into the cosmos, seeding the next generation of stars and planets. What is left behind after a supernova is one of the most extreme objects in the universe, a stellar corpse of unimaginable density. For stars within a certain mass range, the core collapse is so intense that it crushes protons and electrons together to form a sea of neutrons, a process called neutronization. The result is a neutron star. These objects pack a mass greater than our Sun into a sphere only about 20 kilometers, or 12 miles, in diameter. They are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth. They are supported against total collapse into a black hole only by a quantum mechanical effect known as neutron degeneracy pressure. Due to the law of conservation of angular momentum, the collapse from a star many thousands of kilometers across to a sphere just 20 kilometers wide causes the neutron star to spin at incredible speeds, up to several hundred times per second. The collapse also amplifies the original star's magnetic field to extreme levels. If this powerful magnetic field is misaligned with the star's spin axis, it can channel intense beams of electromagnetic radiation out from the magnetic poles. As the star rotates, these beams sweep across space like a cosmic lighthouse. If one of these beams happens to sweep across Earth, our radio telescopes detect a regular, repeating pulse of radiation. We call such an object a pulsar. Most of the neutron stars we have detected are pulsars, their rhythmic beats a constant reminder of their violent birth. While all pulsars are extreme, a small fraction of neutron stars are born as true galactic beasts. These are the magnetars, objects with magnetic fields 1,000 times stronger than a typical pulsars, and a quadrillion times stronger than Earth's magnetic field. This unimaginably powerful magnetic field, not the star's rotation, is the source of its energy, which it releases in occasional violent flares. A recent and revolutionary discovery has revealed that these flares may be responsible for solving one of cosmology's oldest mysteries, the origin of the heaviest elements. We are made of star stuff, but for decades, the origin of elements heavier than iron, like gold, platinum, and uranium, was not fully understood. We knew they were formed in a set of nuclear reactions called the R process, or rapid neutron capture, which requires an environment incredibly rich in neutrons. The merger of two neutron stars was confirmed as one source in 2017. But now, a new source has been identified. The immense stress from a magnetar's twisting magnetic field can fracture its solid crust, triggering a starquake. This event unleashes a colossal flare, and new research, analyzing archival data from a flare in 2004, suggests that these eruptions create the perfect conditions for the R process, forging and ejecting vast quantities of heavy elements in mere seconds. This discovery not only provides a new source for the universe's precious metals, but may also explain why these elements appear so early in cosmic history, before neutron-star mergers would have been common. As if these objects weren't mysterious enough, recent observations have challenged our basic understanding of how they form. Astronomers have found a magnetar, known as SGR 0501 plus 4516, that appears to be a runaway, speeding through the galaxy without any associated supernova remnant. This suggests it was not born in a standard stellar explosion. Alternative formation channels are now being considered, such as the merger of two lower-mass neutron stars or the accretion-induced collapse of a white dwarf in a binary system. This latter scenario could also provide a new explanation for some of the enigmatic and powerful fast radio bursts detected from across the cosmos. These exotic stellar corpses are not just dead cinders. They are active and extreme physics laboratories. By studying their properties, their mass, spin, and magnetic fields, we can test the laws of physics under conditions of density and pressure that are impossible to replicate on Earth, pushing the boundaries of our knowledge about gravity, magnetism, and the fundamental nature of matter itself. From the densest objects in the universe, we now turn our gaze to the most luminous. In the 1950s and 60s, astronomers using the first radio telescopes detected powerful sources of radio waves that, in optical telescopes, looked like faint star-like points of light. They were dubbed quasi-stellar radio sources, or quasars. We now know that these are not stars at all. They are the intensely brilliant cores of very distant, and therefore very young, galaxies. A quasar's incredible luminosity, which can outshine its entire host galaxy by a factor of 10 to 100,000, is powered by one of the most extreme engines in the cosmos, a supermassive black hole. At the center of most, if not all, massive galaxies, including our own Milky Way, lurks a supermassive black hole, a gravitational monster with a mass of millions to billions of times that of our Sun. When vast quantities of gas, dust, and even entire stars are drawn in by its gravity, they don't fall straight in. Instead, they form a swirling, flattened structure called an accretion disk. As the material in this disk spirals inward, extreme gravitational and frictional forces heat it to millions of degrees, causing it to glow with unimaginable brightness. This superheated, luminous disk is the heart of a quasar. This process is also responsible for launching powerful, narrow jets of material that blast out from the black hole's poles at nearly the speed of light. Because quasars require such an enormous amount of fuel to power their brilliance, they are thought to be ignited during periods of intense galactic upheaval, most notably when two galaxies collide and merge. Such mergers were far more common in the early, more crowded universe, which is why the quasars we see are all at immense distances, their light having traveled for billions of years to reach us. The discovery of quasars led to a profound realization. A galaxy and its central black hole are not independent entities. Astronomers have observed a tight correlation between the mass of a galaxy's central bulge of stars and the mass of its supermassive black hole. This suggests that the two grow together in a symbiotic dance, a process called coevolution. This relationship appears to be self-regulating. The powerful outflow of energy from a quasar, known as quasar winds, can sweep through the host galaxy, heating and blowing away the cold gas needed to form new stars. This process, called feedback, can effectively shut down star formation, limiting the growth of the galaxy, which in turn limits the fuel supply available to the black hole. For years, this model of lockstep growth seemed to fit the data. But recent observations from the James Webb Space Telescope are now challenging this simple picture, providing our first clear look at the relationship between black holes and galaxies in the universe's infancy. This has reignited a long-standing chicken or egg question. Which comes first, the galaxy or its black hole? JWST has observed some of the most ancient quasars, seen as they were in the first billion years after the Big Bang, and found that their central black holes are far more massive relative to their host galaxies than what we see in the modern universe. Today, a typical supermassive black hole's mass is about 0.1% of its host galaxy's stellar mass, a ratio of 1 to 1,000. In the early universe, JWST has found quasars where this ratio is closer to 1 to 10. This is the first direct observational evidence that in the primordial cosmos, the supermassive black holes grew first, gorging themselves on gas before their host galaxies had time to catch up. This implies that the initial seeds of black holes in the early universe may have been much more massive than our theories predicted, a major new clue in the puzzle of galaxy formation. As if that weren't puzzling enough, JWST has also found ancient, massive quasars that appear to be surprisingly lonely. The merger-driven model predicts that quasars should be found in crowded environments, surrounded by other galaxies that can provide fuel through collisions. Yet, JWST has spotted powerful quasars from the early universe that are drifting in cosmic voids, with very few neighbors. This is like finding a raging bonfire in the middle of a desert with no trees in sight. If there are no galaxy mergers to provide fuel, how did these lonely black holes grow so big, so fast? It suggests that our models for fueling black holes are incomplete. Perhaps streams of cold, primordial gas can flow directly into galaxies along the filaments of the cosmic web, bypassing the need for mergers. Or perhaps it points to a more fundamental piece of the black hole growth puzzle that we have yet to uncover. The era of JWST is transforming our understanding of the cosmic dawn, revealing a universe where monstrous black holes grew faster and perhaps through different mechanisms than we ever thought possible. The puzzles of our own solar system and the cosmic menagerie of stars and galaxies are profound, but they all concern things we can, in principle, see. We now venture into a deeper realm of mystery to confront the secrets of the unseen universe. The first of these is a gravitational ghost that holds the cosmos together. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies. She expected that stars on the outskirts of these galaxies would be moving more slowly than those near the center, just as the outer planets in our solar system orbit the sun more slowly than the inner planets. But that is not what she found. Instead, the stars on the edges of galaxies were orbiting just as fast, if not faster, than the stars closer in. According to the laws of gravity, these rapidly moving outer stars should have been flung off into intergalactic space. The only way they could be held in their orbits is if the galaxy contained far more mass than could be accounted for by its visible stars, gas, and dust. This was the first strong evidence for a vast, invisible halo of what came to be called dark matter. Since Rubin's pioneering work, the evidence for this mysterious substance has become overwhelming, coming from multiple independent lines of inquiry. Observations of galaxy clusters show that the individual galaxies within them are moving far too quickly to be held together by their collective visible mass alone. An enormous amount of dark matter is required to provide the necessary gravitational glue. The most stunning visual proof comes from the Bullet cluster, which is actually two galaxy clusters that have collided and passed through each other. The hot, visible gas from the two clusters interacted and slowed down, remaining in the center of the collision. However, using the technique of gravitational lensing, astronomers mapped the total mass of the system and found that most of the mass, the dark matter, passed right through the collision without interacting, separating from the visible matter. Gravitational lensing itself provides another powerful pillar of evidence. According to Einstein's theory of general relativity, mass warps spacetime, causing light to bend around it. By observing how the light from distant background galaxies is distorted and magnified by foreground galaxy clusters, astronomers can create a map of all the mass in the cluster, both visible and invisible. These maps consistently reveal vast halos of dark matter that perfectly match the lensing predictions. Finally, the most precise evidence comes from the afterglow of the Big Bang, the cosmic microwave background, CMB. The CMB is not perfectly uniform. It has tiny temperature fluctuations that represent the seeds of all future structure. The specific pattern and size of these fluctuations can only be explained if the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. Dark matter is not just a missing ingredient. It is the fundamental architect of the cosmos. In the standard model of cosmology, tiny quantum fluctuations in the primordial universe were stretched to astronomical scales by cosmic inflation. These fluctuations created regions of slightly higher density in the dark matter. Over cosmic time, these denser pockets of dark matter acted as gravitational seeds, their immense gravity pulling in ordinary gas and dust, which then collapsed to form the first stars and galaxies. This hierarchical bottom-up process created the vast, web-like structure of the universe we see today, with galaxies and clusters forming along immense filaments of dark matter, surrounding vast cosmic voids. Without this invisible scaffolding, there would not have been enough gravity to form galaxies, stars, or planets. Without dark matter, we would not exist. Despite the overwhelming evidence for its existence, the identity of the dark matter particle remains one of the greatest unsolved mysteries in all of science. We know what it isn't. It is not made of protons and neutrons, the stuff of ordinary matter. It is some new, unknown particle that does not interact with light. The hunt to find this particle has led to the development of some of the most sensitive experiments ever built. Physicists have several leading candidates. The most popular for many years have been weakly interacting massive particles, or WIMPs. These are hypothetical particles predicted by theories like supersymmetry that would interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Other candidates include axions, which are extremely light particles originally proposed to solve a problem in the theory of the strong nuclear force, and sterile neutrinos, a hypothetical fourth type of neutrino that doesn't interact via any of the fundamental forces except gravity. The search for WIMPs has driven a global race to achieve the first direct detection. To do this, scientists have built massive detectors deep underground, using the Earth itself as a shield against cosmic rays and other background radiation that could mimic a dark matter signal. Experiments like LUX Zeppelin, LZ, in South Dakota and XENONNT in Italy used large, multi-ton tanks of ultrapure liquid xenon as their target. The idea is that, very rarely, a WIMP from our galaxy's dark matter halo will pass through the Earth and the detector and collide directly with a xenon nucleus, producing a tiny flash of light and a few free electrons that can be detected by sensitive sensors. Recently, both the LZ and XENONNT collaborations have released the results from their most sensitive runs to date. After analyzing hundreds of days of data, neither experiment has found any evidence for WIMPs. These null results have placed the most stringent constraints ever on the properties of WIMPs, ruling out a vast portion of the parameter space where many popular theories predicted they should exist. This sustained lack of detection, despite decades of searching with ever more sensitive experiments, has created a crisis for the WIMP paradigm. WIMPs were long considered the frontrunner because they arise so naturally from theories like supersymmetry, but their continued absence is forcing physicists to seriously reconsider alternative candidates like axions. The era of the WIMP may be drawing to a close. Furthermore, the sensitivity of these experiments has now reached a fundamental barrier known as the neutrino fog. The experiments are now so sensitive that they are beginning to detect a background hiss from coherent scattering of neutrinos from our own sunday. This neutrino signal is, for all practical purposes, indistinguishable from the signal that would be produced by a light WIMP. This means that to push the search for dark matter further, scientists must first perfectly characterize this neutrino background. This highlights a deep interconnectedness between the universe's greatest mysteries. The search for one elusive particle, the WIMP, is now fundamentally limited by our understanding of another, the neutrino. Even in failure, however, there is success. These detectors, built to find dark matter, are now providing the world's most sensitive measurements of exotic neutrino properties, such as the neutrino magnetic moment, pushing the frontiers of particle physics in unexpected directions. The hunt for dark matter continues, but the path forward is now shrouded in a fog of neutrinos, forcing us to be more creative than ever in our quest to identify the gravitational ghost that shapes our universe. The discovery of dark matter revealed that most of the matter in the universe is invisible. But in 1998, an even more shocking discovery revealed that most of the energy in the universe is also hidden, and it is driving the cosmos apart. For most of the 20th century, cosmologists debated the ultimate fate of the universe. The question was simple: is there enough matter, and therefore enough gravity, to halt the expansion that began with the Big Bang and cause the universe to collapse back on itself in a big crunch? To answer this, two independent teams of astronomers set out to measure the deceleration of the cosmic expansion. They used type Ia supernovae as their measuring sticks. These exploding white dwarf stars are incredibly useful because they all detonate with nearly the same intrinsic brightness, making them standard candles. By measuring how faint a distant supernova appears, astronomers can calculate its distance. By measuring its redshift, they can calculate how fast it is moving away from us. The expectation was that very distant supernovae would appear brighter than their redshift would suggest, indicating that the expansion of the universe was faster in the past and has been slowing down over time. What both teams found was the exact opposite. The distant supernovae were fainter than expected, meaning they were farther away than they should be. The only way this could be possible is if the expansion of the universe is not slowing down, but is inexplicably accelerating. The universe is running away with itself. This discovery, which earned the 2011 Nobel Prize in Physics, implied the existence of a mysterious, repulsive force permeating all of space, a force that has been dubbed dark energy. What is this dark energy that makes up nearly 70% of the universe? There are two leading theories. The simplest explanation is that dark energy is a fundamental, intrinsic property of space itself. This is the cosmological constant, represented by the Greek letter lambda, which Albert Einstein originally added to his equations of general relativity to create a static universe. In this view, dark energy is a form of vacuum energy, with a constant density everywhere. As space expands, more space and thus more vacuum energy is created, driving the acceleration. This is the standard view, incorporated into the lambda CDM model of cosmology. Its greatest weakness is the fine-tuning problem. Our best theories of quantum physics predict a vacuum energy that is an astounding 120 orders of magnitude larger than what we observe. For the cosmological constant to be so small, it must be almost perfectly cancelled out by some other unknown effect. An alternative idea is that dark energy is not constant, but is a new, dynamic energy field, dubbed quintessence, that can change in both time and space. This would mean the strength of dark energy could have been different in the past and could change in the future. While more complex, this model avoids the severe fine-tuning problem of the cosmological constant. Recently, the Dark Energy Spectroscopic Instrument, DESI, has provided tantalizing, though not yet conclusive, hints that the density of dark energy may be weakening over cosmic time, which would lend support to the quintessence model. This debate is at the heart of the biggest puzzle in modern cosmology, a profound discrepancy known as the Hubble tension. The problem is a conflict between two independent ways of measuring the universe's current expansion rate, the Hubble constant, h0. When astronomers use the local distance ladder, measuring the distances to nearby Cepheid variable stars and type Ia supernovae, they arrive at a value of about 73 kilometers per second per megaparsec. However, when a different team of astronomers predicts the expansion rate based on a detailed model of the early universe, using data from the cosmic microwave background as measured by the Planck satellite, they get a value of about 67 kilometers per second per megaparsec. Both of these measurements are incredibly precise, and their error bars do not overlap. The discrepancy is now at a statistical significance of over 5 sigma, meaning there is less than a 1 in a million chance that it is a fluke. This is not just a numerical disagreement. It is a crisis in cosmology. It is the most significant observational crack in our standard model of the universe, the lambda CDM model. It strongly suggests that one of the fundamental assumptions of that model, perhaps the nature of dark matter or dark energy, is wrong. The most promising theoretical solutions involve some form of early dark energy, a component that was active in the primordial universe, briefly accelerating its expansion before the CMB was released, which could reconcile the two measurements. The Hubble tension is the loose thread that, when pulled, could unravel our entire understanding of the cosmos. The nature of dark energy is not just an academic puzzle. It will determine the ultimate fate of the universe itself. The cosmos is the stage for a grand tug-of-war between the attractive force of gravity, which pulls matter together, and the repulsive force of dark energy, which pushes space apart. The final outcome depends entirely on which force wins. This has transformed one of the most profound philosophical questions into a matter of active scientific observation. By measuring the properties of dark energy, we are measuring the fate of the universe. There are 3 primary scenarios. The first, and currently most favored, is the Big Freeze, or heat death. If dark energy is a cosmological constant, its repulsive force will continue to dominate gravity, and the expansion will accelerate forever. Over billions of years, galaxies will recede from one another until the sky of any given galaxy is empty of all others. Star formation will eventually cease as the supply of gas is exhausted. Existing stars will burn out and die, leaving behind a cold, dark universe of black holes, neutron stars, and black dwarfs. The universe will slowly approach a state of maximum entropy and a temperature of absolute zero, a cold, empty, and silent end. The second, more dramatic possibility is the Big Rip. This would occur if dark energy is a phantom form of quintessence, whose density increases as the universe expands. In this scenario, the acceleration would become ever more powerful. In the final moments of the universe, the repulsive force of dark energy would become so strong that it would overcome all other forces. It would first tear apart galaxy clusters, then galaxies themselves. In the final fractions of a second, it would overwhelm the electromagnetic force, tearing planets and stars apart. Finally, it would overcome the strong nuclear force, ripping apart atomic nuclei and even individual protons and neutrons, ending the universe in a singularity of infinite expansion. The third scenario is the Big Crunch. If dark energy is a form of quintessence that weakens over time, gravity could eventually win the cosmic tug-of-war. The expansion of the universe would slow, halt, and then reverse. The universe would begin to contract, with galaxies rushing toward each other. As it collapsed, the universe would become hotter and denser, ending in a fiery singularity, a mirror image of the Big Bang. For a long time, this scenario was considered unlikely due to the evidence for acceleration. However, the recent tentative hints from the DESI survey that dark energy may be weakening over time have brought the Big Crunch back into the realm of possibility. Our ultimate destiny is not yet written. It is a parameter that we are actively measuring, a secret that the universe has yet to fully reveal. Our journey into the unseen has revealed a cosmos dominated by dark matter and dark energy, forces that shape the universe's structure and seal its fate. But to understand these mysteries, we must travel back to the very beginning, to the origin of the universe itself, and examine the echoes of creation that still reverberate through space today. The prevailing scientific theory for the origin of the universe is the Big Bang. This theory states that approximately 13.8 billion years ago, the entire observable universe was concentrated into an incredibly hot, dense point. From this initial state, it began to expand and cool, a process that continues to this day. There are two powerful, independent pillars of evidence that support this model. The first is the cosmic microwave background, or CMB. In the first 380,000 years after the Big Bang, the universe was an opaque, searingly hot plasma of protons, electrons, and photons, with light trapped in a constant dance of scattering off free electrons. As the universe expanded and cooled, a critical threshold was reached. Protons and electrons were finally able to combine to form neutral hydrogen atoms. This event, known as recombination, made the universe transparent. The photons that existed at that moment were set free to travel unimpeded through space. Today, 13.8 billion years later, we observe this primordial light as a faint, uniform glow of microwave radiation filling the entire sky. This is the CMB, the afterglow of creation. It has a near-perfect thermal blackbody spectrum with a temperature of just 2.725 Kelvin, cooled by the expansion of the universe. A series of space missions has mapped this ancient light with increasing precision. The COBE satellite in the early 1990s made the first detection of tiny temperature variations, or anisotropies, in the CMB. The WMAP satellite in the 2000s measured these anisotropies with enough precision to establish the current standard model of cosmology, the Lambda CDM model. And the Planck satellite in the 2010s created the ultimate map of the CMB, providing the most detailed picture of the infant universe ever made. The second pillar of evidence is Big Bang nucleosynthesis, or BBN. In the first few minutes of the universe, from about 1 second to 3 minutes after the Big Bang, the temperature and density were just right for the first atomic nuclei to form. Protons and neutrons fused together to create the lightest elements. The theory of BBN makes very specific quantitative predictions about the primordial abundances of these elements. It predicts that the ordinary matter in the universe should be composed of roughly 75% hydrogen and 25% helium, 4 by mass, with trace amounts of deuterium, an isotope of hydrogen, and lithium-7. These predictions depend critically on a single parameter, the density of ordinary baryonic matter in the early universe. When astronomers observe the most ancient, pristine objects in the cosmos, such as metal-poor stars and distant quasar absorption clouds, which have not been significantly contaminated by later stellar processes, they find light element abundances that match the predictions of BBN with remarkable accuracy. This stunning agreement between theory and observation provides powerful, independent confirmation of the hot, dense state of the early universe. While the Big Bang theory is incredibly successful, it leaves several profound puzzles unanswered. These puzzles led to the development of a crucial addition to the model, the theory of cosmic inflation. The first puzzle is the flatness problem. Observations, particularly from the CMB, show that the geometry of our universe is flat to an extraordinary degree of precision. According to general relativity, any initial curvature in the early universe should have been magnified dramatically by cosmic expansion. For the universe to be so flat today, its initial density must have been fine-tuned to the critical density to an accuracy of 1 part in 10 to the power of 62, a coincidence so unlikely as to demand an explanation. The second puzzle is the horizon problem. When we look at the CMB in opposite directions on the sky, we are seeing regions that are now separated by nearly 30 billion light-years. At the time the CMB was emitted, these regions were already too far apart to have ever been in causal contact with each other. meaning no signal could have traveled between them. Yet, they are at almost exactly the same temperature. How did they reach thermal equilibrium if they could never communicate? In the early 1980s, physicist Alan Guth proposed a solution: cosmic inflation. He theorized that in the very first fraction of a second after the Big Bang, between roughly 10 superscript 3 and 10 superscript 3 superscript 2 seconds, the universe underwent a period of hyper-accelerated exponential expansion, growing by a factor of at least 10 superscript 2. This brief but stupendous growth spurt elegantly solves both problems. It solves the flatness problem by stretching the fabric of spacetime so immensely that any initial curvature would be flattened out, just as inflating a tiny, wrinkled balloon to the size of the Earth would make its surface appear perfectly flat from any local perspective. It solves the horizon problem because the regions we now see on opposite sides of the sky were in close causal contact before inflation began. They were a single, tiny, uniform patch that was then stretched to encompass our entire observable universe and beyond. Inflation does more than just solve old problems. It makes a profound new prediction. It provides the origin for all the structure we see in the universe today. According to quantum mechanics, even a perfect vacuum is not truly empty, but seethes with tiny, random quantum fluctuations. During inflation, these microscopic quantum fluctuations in the primordial energy field were stretched to astronomical sizes, becoming macroscopic density variations. These tiny density ripples, imprinted on the universe, were the seeds of cosmic structure. Over billions of years, gravity caused matter to clump together in the slightly denser regions, forming the first stars, galaxies, and the vast cosmic web. The statistical properties of the temperature anisotropies in the CMB, as measured with incredible precision by the Planck satellite, are in stunning agreement with the predictions of the simplest inflationary models, providing our strongest evidence that this incredible event really happened. The ultimate smoking gun for inflation would be the detection of a specific swirling pattern in the polarization of the CMB, known as B-modes, which would be the signature of primordial gravitational waves generated during the inflationary epoch itself. The search for these faint ripples in spacetime is a primary goal of modern cosmology. The theories of the Big Bang and inflation describe the origin of our universe and the seeds of its structure. But they also raise a deeper question. If our universe could be created, could there be others? This question has moved from the realm of philosophy to science with the discovery of exoplanets, planets orbiting other stars. The exoplanet revolution has revealed that planets are not a rare exception but a common feature of the galaxy. Thousands have been discovered using a variety of ingenious techniques. The most successful technique to date is the transit method. This involves monitoring the brightness of a star and looking for a tiny, periodic dip in its light, which occurs when an orbiting planet passes in front of it from our point of view. Space telescopes like Kepler and the Transiting Exoplanet Survey Satellite (TESS) have used this method to discover the vast majority of known exoplanets. The second major technique is the radial velocity method, which looks for the gravitational wobble a planet induces in its host star. As the star is tugged back and forth by the planet's gravity, its light is alternately blue-shifted and red-shifted. By measuring this Doppler shift, astronomers can infer the presence of a planet and estimate its minimum mass. A third method, gravitational microlensing, uses the gravity of a foreground star and its planet as a lens to briefly magnify the light of a much more distant background star. This can reveal very small planets or even rogue planets that drift through space untethered to a star, but the lensing events are unique and non-repeatable. Finally, the most challenging but also most direct method is direct imaging, literally taking a picture of the planet. This is incredibly difficult because the planet is billions of times fainter than its host star. It requires sophisticated instruments called coronagraphs to block the starlight, and has only been achieved for a handful of large, young planets that are far from their stars. The James Webb Space Telescope recently captured a stunning direct image of the exoplanet HIP 65426b, heralding a new era for this technique.